Hi everybody, 9.4 is the logistic equation, and most of this pertains to looking at a population growth. Essentially, the simplest model for population growth has always been dy over dt equals k times y. But that suggests that these populations grow exponentially, and of course that's not true, right? A population cannot increase without limit. There's lots of things to take into account, such as food scarcity, competition between species, etc. So a widely used model is this logistic differential equation. Dy over dt equals k times y times the quantity of 1 minus y over a, where a is considered what's called the carrying capacity, kind of like a max population, so to speak. Remember that, so this was new for me as well, but remember that dy over dt, right, can be notated by, or denoted by, that y with the dot above it. So that's going to be really common here. I tend to just replace it with dy over dt because it's something that we've been working with all along. Conceptually, right, this whole term of 1 minus y over a is almost non-existent in a sense as long as y is small relative to a, right? If y is really, really small over a, that term zeroes out, and therefore that set of parentheses is essentially 1, and this is approximately equal to k times y. So it follows that exponential growth where it should, right? And then when we do get to the extremes, that's when it starts to level it out for us. So we're just going to go through a couple of examples, two examples here. One is just the straightforward with an equation given, no circumstances, no word problem, but just straightforward. So this section, especially if you follow along in the textbook, is very much equation driven. There are multiple layers of this equation that you could kind of pause and use if you choose to, but you can also just default back to these two that I have up top here, right? The differential and then that general solution, right? So example 1, solve y dot, or dy over dt, equals 0.3 y times the quantity 4 minus y with an initial condition of y of 0 is equal to 1. So the first thing is we want to make it fit our differential, right? So I'm going to say that dy over dt, as given, is equal to 0.3 y times 4 minus y. And it is equivalent to ky times 1 minus y over a. But we need to fit this format. So the first thing we need to do is we need to factor that 4 out so that the first term in the set of parentheses is a 1. So this is equivalent to 1.2 if I take away the 4 times 1 minus y over 4. And now we can see explicitly what our k is and what our a is. That was our whole job right now. So the k value is 1.2 and the a value is equal to 4. Okay, so from this we can come up with our general solution. Our general solution is y 4 divided by 1 minus e to the negative 1.2t divided by c. Right, that is that unknown constant that we need to solve for. So we are given an initial condition of 0, 1 essentially, is our ordered pair, and that allows us to solve for c. So the textbook does walk us through this optional method using the fact that c is going to equal y sub 0 over y sub 0 minus a. Now, that's extremely easy, right? But to me, that's a little overwhelming just because it's another formula to memorize in what could be a relatively simple problem. So you can use it, of course. C in this case ends up being 1 over 1 minus 4 equals negative a third. Great, we would just take that and put it back in. But there's also no reason that we can't solve this from start to finish. So if we take 0, 1 and we plug it into our general solution, so we would then have 1 is equal to 4 divided by 1 minus e to the negative 1.2 times 0 power, so e to the 0, divided by c. So that makes this pretty manageable. I chose to obviously evaluate the e to the 0 as 1, and then I took that whole denominator and multiplied it to the left. So I really have 1 minus 1 over c is equal to 4. Okay, then I can subtract my 1. Right, and then I can see if I cross multiply, right, and basically swap the c and the 3, negative 1/3 is then equal to c. So it's the same exact thing. My final step is to take my c and put it into my general solution equation. So I have my solution, y equals 4 over 1. So if I'm dividing by c, I'm dividing by negative 1/3. This turns into a plus 3e to the negative 1.2t would be my final answer. Okay. The second one, a little bit of context. Now we're looking at a deer population, pretty relevant for the town of Princeton in particular. So a deer population grows logistically with growth constant k is equal to 0.4, year to the negative first, in a forest with a carrying capacity of 1,000 deer. All right, so find the deer population, P of t, if the initial population is 100. So we are looking for P of t. We are given k, which is 0.4, and we are given a, 1,000. It's like our max. So therefore, you can either use P dot, I'm not even positive that's the best way to say it, but anyways, dP over dt equals 0.4 P times quantity, 1 minus P, standing for population, of course, divide by the max, 1,000. Okay. And then our general solution would be P of t equals 1,000 divide by 1 minus e to the negative kt, so negative 0.4t divided by c. Okay. So we are given that initial condition. We're given 100. So again, you can use both ways. This time I did my work using that shortcut, but I'm going to do it both ways for us. So c is equal, here's your shortcut, of 100 of the initial over initial minus carrying capacity of, oops, too many zeros. So we get negative 1/9 for our c. But I'm sure we could solve this normally. So P of t, we are looking for when does it equal 100? For 1 minus e to the 0, so that's going to be a 1 over a c. So then I'm going to do 100 times 1 minus 1 over c equals 1,000. So then if I divide by 100, right, then I have 10. And I subtract my 1, I have 9. And I move things around, of course I get my negative 1/9. Okay, so it's really not so bad, especially with an initial condition where that t is 0, the e to the 0 always goes to 1, so it's not so bad. Anyway, so now my equation becomes P of t is equal to 1,000 divided by 1 plus 9 e to the negative 0.4 t. Okay. So part B says, well, how long does it take for the deer population to reach 500? So we take our equation that we just found, set it equal to 500, and solve. Again, the textbook shows a way to use a different variation of the equation. There's really no need. Feel free to check it out, follow along. Maybe it makes more sense to you. But for me, I'm just going to take the equation that I already made, set it equal to 500, and solve it. So I'm going to multiply by that denominator. I divide by 500. So I have 2. And then I can subtract 1 and divide by 9. So I have e to the negative 0.4t equals 1/9. So if I apply the ln at this point, we'll have negative 0.4t equals ln of 1/9, which will come out to be negative because it's a fraction there. And I divide that by negative 0.4. Certainly go to your calculator, and that would be approximately 5.5 years. Okay. So these two examples would be your in this section. There's nothing else to it, so here's just a quick summary of kind of those three equations that we worked with. Again, this is optional, but these are the two that I worked with in order to solve for these conditions.